go through this thing. The last part is the one that some people have trouble with, but it was meant to be a very straightforward thing. So now, can you check and make sure you can view the solutions? You got it? Got it? All right. So for this problem, let's go through this. We had, for part one, we had a power density, an average power density equal to 20 watts per meter squared, right? This is propagating an error. Y'all see that? Part one? Very first one. All right, so if we have this, we know average power, if it's a lossless material, and an air especially, is just 1/2 times the magnitude of the electric field squared over eta naught. And eta naught is just 120 pi, right, ohms? So to get the E field, it's going to be just magnitude of the E field. It's the square root of 2 eta naught times P average. And you can do this, just put in 125 times 20 times 2. And I want to say it's 133, but I don't remember exactly. Can you tell me what it was? 122?
Yeah.
122.8, and that's volts per meter. And likewise, you can get the magnitude of the H field by simply saying its magnitude of the E field over eta naught. And I want to say that is it 328 or 326? And this is going to be amps per meter. All right, those two are straightforward, just to make sure you knew the basics. Then the next part of the problem, it says a media has conducting properties. This is part 2. And it says sigma is equal to 5, epsilon relative equal to 72. F is, help me out here, 300 megahertz, is that right?
Yes.
300 megahertz. And they want the propagation constant, and mu relative is equal to 1. The propagation constant and the intrinsic impedance, right? So for these, this is simply being familiar with the formulas. This is J omega mu times sigma plus J omega epsilon. And here, epsilon is equal to epsilon naught, epsilon r, or it's 72 times epsilon naught. Omega is 2 pi times F, or it's going to be 600 pi times 10 to the 6th. And when you do the whole thing, you're going to get 2 values. The real part, I believe, is 68 roughly plus J86. I believe that's about right. You can take a look. In the solution, did you all get that, guys? It's point something, but I'm just, so that's what gamma is. And eta, the formula is square root of J omega mu over sigma plus J omega epsilon. Here, this one you couldn't assume was a good conductor or a very lossless dielectric, or a very unlossy dielectric. It was both. You had to run the numbers on this one. And for this one, it comes out to be, and I think I left my solutions down. Can you give me the real and imaginary? It's like 13 plus J, or 16 plus J 13? 16 plus J 13, roughly, right? If you put magnitude and angle, it's fine too. It's 51 degrees, I think. The angle, and I forgot what the magnitude was, but. So that was eta. Then finally, for the last part, I wanted to know how thick a material had to be. So I don't know the thickness, but I know it's made of copper. And the conductivity of copper is 5.8 times 10 to the 7th and it's Siemens per meter, 1/ohm meters. And I want to know it so I get a shielding effectiveness equal to 100 dB. That was the question, right? So there's a couple of things we need to get the actual fitness. First, we have to calculate the value of the impedance of the shield, or this is going to be the impedance of the copper, which is square root of J omega mu over, and this one you can just put in sigma, because the J omega epsilon. Sigma is so high, omega epsilon is just nothing, effectively. You can put it in, but you get the same value. And this, I'm trying to think of the back point. Is it 0.026 plus J 0.026, or just give me the magnitude if you want. I know the angle is 45 degrees.
Yeah, I got roughly 0.026 times 10 to the power or something.
0.026 plus J 0.0, or the
Yeah.
magnitude? All right, you can correct me if I'm wrong. 0.026 plus J 0.026. It's in the solutions. Is that, are you looking on the solutions? Is that what I have? I don't remember exactly. Last part, copper. Is it there or not?
0.012.
Total? Oh,
Or 0.008 plus 0.008.
okay, sorry. All right, 0.008 plus J 0.008. And what's the magnitude of that?
0.012.
0.012 at an angle of 45 degrees, right? Okay, so that's the shield impedance in ohms, right? Now, after that, what we need is the reflection coefficient 1, and that would be here. And the reflection coefficient is the impedance you're going into. This would be an eta shield. And this is going to be eta naught. This is eta naught. So it's going to be eta shield minus eta naught over eta shield, or sorry, we want transmission coefficient, my bad. Transmission coefficient in 1, let me do it this way. And then we need the transmission coefficient in 2 is equal to 2 eta shield, it's always twice the impedance you're going into, over eta shield plus eta naught. This is a small value, but here you can almost ignore eta shield down there. It's really 2 eta shield over eta naught. You all follow me? Because eta shield is so much less than this. You all follow me now? And can you just tell me what that is? I have it there, don't I? Tau 1, TAU1.
4.377 times 10 to
10 to the minus 5.
And then plus that same number, imaginary.
Yeah. And what's the magnitude?
6.19.
Times 10 to the minus 5.
Yes, sir.
At an angle of 45 degrees. I know that's going to be the case. So that's tau 1. Now tau 2, I'll do it right here. Tau 2 will be twice the impedance you're going into over the impedance you came from plus the impedance you're going into. Y'all remember what I said this is going to be for good conductors? About 2, right? Because here, eta shield is so much less than eta naught. It's just eta naught. Eta naught by eta naught cancels, you get 2, about 2. So now, and I'll work over here. Now what I'm going to do is take the definition of shielding effectiveness. Remember, this is with voltage, not power, which is 20 times the log. That's a base 10 log of the magnitude of tau 1, right, times, and actually it's minus this, tau 1 times tau 2, right? And then it's going to be times e to the minus alpha z. Now, the reason I put the minus sign there, I'm just trying to explain this, is because I know really with Wentworth's book, he has 1 over this quantity, right? And 1 over the log A is equal to minus log A. Y'all follow me on this? So I just made it like this to make it easy, okay? So when we do this, we find we take 10 to the power and it's minus shielding effectiveness divided by 20. Let me tell you what I'm doing. First, I divide by 20, put a minus sign, so I get rid of that. Then I have to take everything to the power 10. Then I divide this by tau 1, tau 2, right? And then I have to take the natural log of both sides. So I take the natural log of this, and then I divide by 1 over alpha with a minus, and that's going to be the thickness. Do y'all follow me on this? The only thing I'm doing is solving this equation right here that I had, minus 20 times the log of tau 1, tau 2, e to the minus alpha z for z. You follow me on this, guys? All right, it's just an inverse problem. I give you the shielding effectiveness, you tell me the thickness. One gives the other. They're linked. So when you do this, let's see. I'm sorry, I don't know. 5 points. I want to say it's 56.
5.644 times 10 to the negative 5.
Right, it's 50, about 56 microns. Now, if you want to, you can take 56 microns and you can go to the definition of shielding effectiveness. And I didn't calculate alpha, but alpha for this one, I got tau 1 and tau 2, but you know that alpha is equal to beta for a good conductor, and this is sigma of the copper is much, much greater than omega epsilon. So that's equal to the square root of J omega mu, right, times, well, let me do it this way. It's just going to be equal to pi f mu sigma, right? That's the one that we talked about. It's 1 over skin depth is alpha. It's the square root of pi f mu sigma. And it's a big number. You can give that to me if you want. I forgot what it is. Huh?
4.735 times 10 over 5.
4.7, what was it?
785
785?
times 10 to the 9.
10 to the 5th, yeah, that's right. Napier's per meter. An enormous amount of attenuation, okay? And that's sort of it in a nutshell. Now that quiz, if you haven't had me before, I'm just going to clue you. It's all based on the previous homeworks and what we talked about. There's nothing I'll throw at you that's out of left field, all right? So if you do the homework, you understand it well, you should really just glide through these quizzes without any problem at all. It's meant to be that way. Do y'all recognize everything here? Right, any questions at all? The only thing you might have stumbled over is the shielding effectiveness because it was an inverse problem, but you got to be, as engineers, familiar with that, okay? If you made a mistake, don't worry. The lowest quiz I drop, and usually, well, there are some people that get perfects everywhere. Most people have one bad day. Most, not all. There are people I've had in a class that didn't miss a point, but that's the rarity. I had one really good student. He just got his PhD from Harvard, and he's going to work on one. He's super bright. His name is Sung-Yo Kim. You'll be reading about him. He did. He was at MIT and Harvard, but he did it's neural network and genetic algorithm optimization of biosystems. So some Wall Street firm must be somebody who's doing front-end stuff with biosystems and nanotechnology, hired him. I don't know how they hired him, but they probably paid him about 30 times what I did. But he was one of those guys that he didn't miss anything ever. And there are people like that. Okay. So now, last time we talked about waveguides. All right, we're talking about conducting waveguides. I'm going to give you a summary, and I'm going to try to do this from a perspective if I was sitting where you were. All right, we were talking about PM mode and waveguides on Friday. PM means that HZ equals 0. And just to review, when we talk about waveguides, this is in Dr. Wentworth's book. The horizontal dimension is A, and this would be the x-axis, here would be the origin. The vertical dimension is B, and Z technically is coming out of the page, but that's the cross section. And it's a good conducting guide. It means the guide itself has walls that are made of metal. If you want to, after class, follow me upstairs and I'll show you pieces of waveguide. How many have seen waveguide? You have? Waveguide is very, very common. If you look in your microwave oven, there's a waveguide that goes from the actual cavity in there that you close to the, I want to say it's a magnetron anymore. I don't. It's probably a magnetron. It creates the energy. And if I have time, I'll get into that. It's kind of interesting. So, and just for the fact, the waveguides, I mean, magnetrons and waveguides were the key to radar that really allowed World War II to be won by the British/Americans. Because if we didn't have radar, forget the A-bomb, we would have had nothing. We would have been destroyed. And radar made it a doable thing so the British Spitfires, I've got a whole spiel on this when I teach my radar class. I show them when they got radar, they could get their fighters up there, these little Spitfires up there before the Luftwaffe got over and started bombing. And they literally, this little group of people stopped this massive German assault. And it was pretty amazing. Anyway, it was done by radar and the magnetron. So that's the dimensions, and for TM, H equals 0, and we found out that E in the Z direction was equal to some scalar value, we just call it E naught, times the sine of M pi over A times X times sine of N pi over B times Y times E to the minus J beta, and I call this beta Z, Dr. Wentworth just leaves it as beta, times Z. That's the Z component. Here, beta Z is equal to beta unguided, and beta unguided is equal to omega square root of mu epsilon times the square root of 1 minus quantity F C over F squared. I want to also say that with waveguides, they're high pass filters. Do you all remember that? You got to get to a certain frequency exciting them or else nothing passes. And the cutoff frequency for the waveguide, do you remember we do this? There's several things we did, but the cutoff frequency for a guide, and the cutoff frequency is different for different modes. And the modes are dictated by the values of M and N. The cutoff frequency is really going to be the speed of light, or C, divided by the square root of epsilon relative, divided by 2. And then it's going to be times square root of 1 minus FC over F squared. Now, I'll just tell you where this came from is normal. Do you remember when we did separation of variables, we had beta x squared plus beta, or sorry, minus beta x squared, minus beta y squared, minus beta z squared, plus beta unguided, which is right there, squared. That's as if there was no waveguide. All equaled 0 at cutoff, right? Beta z was 0, I'm sorry. So you could solve for the actual cutoff frequencies for the different modes. And that's what it comes down to right here. Now, this is important. That EZ value, not really important. It's important you know there's no 8Z. If it's called a TM mode, it means it's transverse magnetic. There's no magnetic field, the direction is propagated. That's what it means. Everything's transverse or perpendicular to the direction of propagation. The lowest order mode, or the lowest frequency that can be carried in a TM mode, is FC11. So 1, 1 is lowest mode. And the reason is because if you try to get to a 0, 1 or a 1, 0, then the sign of 0, 0, you got nothing. Y'all follow me? So there is no 0, 1 or 1, 0 mode for TM propagation in a rectangular conducting guide. No. The lowest possible frequency will be the 1, 1 mode. And I didn't put this down here, but the cutoff frequencies, let me put it up here. In general, the cutoff frequencies, FC, M, 10. Oh, I'm sorry. This is not the cutoff frequency. This is my bad. Let me put this down here. Cutoff frequencies are going to be equal to the way he does this, and this would be the square root of M over A squared plus N over B squared. I'm so sorry. This should be C, and C is 3 times 10 to the 8 over 2 epsilon relative. And epsilon relative is just the permittivity of the material in the guide. Now, the reason I don't put a square root of epsilon or mu relative is because they're not going to have magnetic conductors. I mean, any magnetic materials. Magnetic materials are inherently very lossy. If you did, then you could replace C over square root of epsilon r with just the velocity of the wave in the guide. But I don't even bother that I leave this one, because usually, I think even Dr. Wentworth's book has this. Now, that gives you the lowest order of the frequency. Therefore, the lowest TM mode that will propagate is when the frequency is 1, 1 here, and that would be C over 2 square root of epsilon relative, and then it would be square root of, really, 1 over A squared plus 1 over B squared. And that would be the lowest order frequency for the TM mode. Y'all hear me on that one? So, yeah.
So is that not just essentially the cutoff frequency? Like, what is the mode?
Yeah, that is the cut. The C means cutoff frequency of the lowest. Sorry, if I didn't make that clear. Cutoff of mode M, N. Now it's the same cutoff frequency if we're in the TE mode. You'll see that.
So what is mode? What do you mean?
That's the value of M and N. I'm going to try to explain this in a way that's meaningful. If M is, say, 2, that means I would have a full wavelength across the horizontal. M is 1, I would have half a wave. This is the way the fields, it's called field mapping. You've got your book, right? Okay, here's a great time to use the book for once. If you go in chapter 7, and you look, I had this down too, on page 390, I believe it is, 392. 392, what you'll see is he shows, what he does is, this is going to be the phasor domain, he takes the cross section of the guide, and it's for the TM modes, the 1, 1, and he shows you what the EZ field looks like in the upper one. You see that? And what he's doing is showing contours of equal value. EZ is always in the Z direction. And the thing is, the closer you get to the middle, the larger the electric field is. But what happens with the EZ mode is you got a half wavelength horizontally in magnitude and a half wavelength vertically. Now,
So the larger the mode, the larger the wave pattern?
No, the larger the values of M and N, the higher the frequency for starters for a given A and B. But then the pattern changes. Then if you look down there just look at, well, look at the second one. It's EY, contours of EY versus position. And what you're going to see, it has, you can't see it very well there. The top one, you can see it though. If you look at EZ, you see how it's a half wavelength from across. It's just, do you have your book or? It's a half wavelength. Well, if it was a 2-0 mode, or I mean a 2-1 mode, then you would have a full wavelength. You would see 2 humps there. And it's called the field mapping, where the way the field is arranged that will allow propagation. Now, I always try to make something analogous to it. I don't know if you've ever looked at how waves are set up. We used to see stuff like this where they take sand and they put it in like a square well, and then they vibrate at a certain frequency, and you would see contours where there'd be piles and then voids, piles, voids, and those had to do with the actual resonant frequency of the cavity. Do you all remember that stuff in physics at all? I don't know if they ever do these things. Well, it's similar to that, but it's the allowable frequency, the way it sets up for a minimal energy. I'm reaching here, but see, the problem with electromagnetics is if you take us, try to see how the field's map. First of all, you say, why are they mapping that way? The reason is they're solving the differential equations, and they're solving in a way that's allowing propagation. And when you solve the diffie-q's, it's going to say that you can only have, I mean, the tangent field on any conductor has got to be 0 if it's the E field, right? And the H field's the derivative of the H field with respect to the normal is 0. Now, I'm not going to get into all this yet. So really what we're doing is when we're solving the diffie-q's and we come up with this, we're saying that this is how more or less nature confines the electric field to develop inside that guy. I don't have a better way to explain it. These are the laws of physics that we found out by interrogating nature. You'll get a better feel in time for this, but you know, here's a fundamental thought. All right? So when we talk about physical phenomena that's non-quantum, everything we describe is in terms of either integral or integral differential equations or just pure differential equations. All the physical laws we know manifest in terms of solutions to the differential equation for electromagnetic fields, as well as any kind of kinematics, the trajectory of a ball, for instance. It's a differential equation you can write in terms of the position of a ball versus, as a matter of fact, just about everything is. So just, this is a little on the side here, hopefully it'll give you a little something to chew on. So there are 4 major forces, right? There's the electromagnetic force, then there's gravity, right? Then there's the weak force, the strong force. Strong force is the little nuclear hooks that hold the protons together so they don't rip apart, because you got 2 positive charges that are so close, these little nuclear hooks, it's called a strong force, hold together. But the thing is, the nuclear force that holds those together is not a 1 over r squared like gravity. It's what, some constants, masses, 1 over r squared. Electric field, some constants over r squared. It's r to the 6th, 1 over r to the 6th. So as soon as you break beyond a certain value, all of a sudden they just rip apart and they liberate immense amounts of energy. Now, do you know what the weak force is? Weak force has to do with how come the universe doesn't move according to just the 3 known forces. We call it the weak force. At great distances, there's something that's inhibiting movement, and that's the weak force. Y'all had, well, you didn't have modern physics though. Now it's theorized by a lot of people. There's this mysterious 5th force. Remember, all the forces that we know about because we measure deflections of stuff. All right, for a mass and gravity, we have a scale that measures the force the mass operates in. We measure the electrical force or voltage that's developed on an antenna. We can figure out electromagnetic field strengths from that. For the strong force, it's a whole different ballgame. you look at the aftermath to measure the actual thing, and then it's theorized what it is, and they construct these solutions. And sure enough, but all of them obey differential equations. This is the neat thing, at the macroscopic level. So have you heard of the unified field theory? So here's the deal, I'm not going to get into it all. If you take the curl of E equation, curl of H, write them down. You can write the gravitational equations in terms of their vector potential. Here's something else. Did I mention? I think I did. Remember I said that the electromagnetic fields are perpendicular to the direction they propagate, right? And then I mentioned something about gravity. Do y'all remember that? I said that gravity itself, it's just, if you think about a gravitational field, it's pulling this way if there are two masses, or it's, right? It's always pulling together. And if I wobble one, you don't think of propagation, but in fact, there are gravity waves, because if you accelerate something at a high rate of speed, you do get an actual gravitational field that's launched, and it solves a differential equation similar to the curl equations for the electromagnetic field. Very hard to measure, but they measured it out in California. And the guy probably is going to get a Nobel Prize for this. They had to use these long, like mile-long things that they measured small deflections with lasers, but they in fact proved that there are gravity waves. I don't know how they proved it. I mean, I know how they basically measured it. I don't know how they proved it. But the deflections, just think about this. Now they're perpendicular to the direction of propagation. So I have these mile-long things, and a gravity wave is coming this way. It's deflecting that bar this way. And I got this little thing, a laser interferometer thing, and they're measuring the deflections up and down at the end of these things, which is amazing. So now they're theorizing about this possible fifth force and the other thing. And the way they're doing it is they take a guess. Here's the differential equations. Based on what we know, we're just taking a guess. And we're going to see if the uncertainties that we see in our measurements can be explained by this diff EQ. And then if we add these constants to fit the measurements, if in fact this works everywhere. Now, there's a long story behind this, but that's sort of what they're doing. That's the power of diff EQ, because it can explain nature. And that's, you know, where I'm sitting where you were, I wasn't that interested in it, but I like these kind of stories because it gave me something to think about at night. I wondered about it. Maybe one of you guys go to Nobel Prize in physics to figure that out. All right, so this right here is basically where we were, I think, for the PM modes on Friday, right? Here's some more stuff that's important for TM. And I should tell you, if you're wondering how they actually get this electromagnetic field energy into a waveguide, here's basically how it happens. If I look at a guide just on the cross section, so energy is propagating this way, what they do is poke a little hole in there, and they put an antenna. It's not deep. It's only maybe a tenth to maybe a quarter of the way in. And that antenna excites the cavity in the mode you want. I'll spend more time on this in a bit. But that's how they get energy in. They literally have that. So it'd be a coax cable coming right here, and the center feed would go down. And that's it. Y'all follow me? Down. You look at that, and you're wondering, well, anytime I see that I'm feeding something, and this is a coax cable, right? Like, it's not drawn very well, but if it's a coax cable, I have to impedance match at a given frequency. And in fact, you do. So a good question is, well, what impedance is it feeling right there? Well, impedance is always a ratio of the E field to the H field, right? Same here, and I'm going to tell you what it is. Now, I'll tell you something else. I just put you EZ there, but because there is no HC, we can get EY. We could go through EY, and he's got it in his book, and we can get this because we can take curl of E. All right, this is easy. So then we'd have J omega mu, and then we could get, let's see, HY here. Or H, let me just put it H field, and we can stick that into the into E is equal to curl of H over J omega epsilon. And I'm not going to do the whole 9 yards, but for EY, it's going to be a constant. It'll actually be beta Z squared over let me just think about this, over beta z squared plus beta unguided squared, and then it's going to be m pi over a, and it's going to be cosine of m pi over a times x times sine of n pi over b times y times e to the minus j beta z times z. And in his book, if you want to know where I'm getting that, oh, sorry, this is n pi over b. This is in his book. You don't need to know all these field components. This is on page 390, and it's equation 7.43 minus beta squared. Sorry. But here's the deal with this. This is just a constant right there. Usually you would just put EY0 or E0Y. You don't have to put all that stuff down because frankly, and I didn't even put the E naught in here, you don't even know what E naught is. So E naught's an uncertainty. That's an uncertainty, but scaled by those beta z squared over beta z minus beta u squared times n pi over b. You don't have to worry about that at all. You see he has all the field components there? The way he gets them is from the curl equation. Now, because there is no HZ, when you do these curl equations, just based on easy, you can come up with all the electric field components. All right, I'm not going to go ahead and do them. They're in there. But I want to tell you this much. The important thing is this. That's the electric field in the z direction. The lowest value is m and n. And now the next thing we have to do is find the actual characteristic impedance that you would feel if you fed that. And the symbol is Z. So this would be the impedance of the guy. Impedance of TM modes. And it's in fixed. So it'd be ZTM M comma N. And that's going to be equal to, and he calls this eta unguided, and then it's going to be times square root of 1 minus the quantity FC for the given mode over F. That's the actual frequency of excitation. Now, eta unguided is equal to the square root of mu over epsilon. Remember, for when you're dealing with free space, and here, the core of the guide, the dielectric inside the guide, is assumed to be a lossless region of Bow. If it's lossy, you're just wasting your time. I mean, it's like, you know, you would not have a lost guide for any meaningful work. So that's sort of this is the intrinsic impedance. And if the idea is this. If you're going to feed a waveguide, you have to make sure that the impedance of that coax cable feeding that is the same as the impedance of the guide for the mode you're feeding. Also, I don't want to spend a lot of time on this, when you're talking about the different modes in the different field structures, here's something that's going to kind of, I don't think Dr. Wentworth would want me saying this right now, but I'm going to anyway. Nobody sends a 1-1 mode down a rectangular guide, usually. You only operate in the 1-0 mode. All right, I'm going to say this, and it would not be a TM, it would be a TE mode. The reason is because for TE mode, once you get over the excitation frequency, only that mode can develop. When you're putting energy into a waveguide like this, if you're at a frequency so you can develop the 1-0 and 1-1 mode, both will develop. All right, and the thing is, I didn't talk about this yet, but the velocity that they propagate is different, which means you would get corruption of the signal integrity. If that happens, then everything's garbled at the other end if you're trying to communicate, because then there is nothing that's going to be coherent about that message. So almost always, everything we use the waveguide for it's going to be in the 1.0 mode, and it'll be TE. So I'm just telling you that right now. TM is not that important. You need to know this because there are certain applications where you want to develop both a 1.1 and a 1.0 mode, and here's why. As that information is coming down the guide, there's a filtering you can do where you can break off the 1.0 mode's energy and leave the 1.1s go, or the 1.0 mode go. So you can literally use one waveguide for 2 channels. Right? But that is rare. First, because you never get 100% of the signal going one way. You get like 95. So there's still that 1% that goes in the other direction, and it causes problems. Just trust me on this one. For most stuff, you don't want anything but a 1.0 mode, and I'm telling you this from practical experience that I've had. This is what you need to know. Next thing is velocity on a guide, right? So there's 2 types of velocity. There's phase velocity and there's velocity of energy. And in a waveguide, as you get close to cutoff, the phase velocity goes to infinity. But the velocity of energy goes to 0. I'm going to try to explain that. Let me go through the TE mode, and then I'll explain the velocity business, okay? Because I think it'll help. So this is sort of TM in a nutshell. Lowest operating frequency is going to be the 1.1 mode, and you get the cutoff frequencies like that. We got any rain in store for us?
It's supposed to storm all the end of the week, but they keep pushing it back like every day. So I don't know.
I'm hoping for rain. I got a lawn that's starting to look good. We have a sprinkler system, but I rarely turn that thing on. Did you guys get on the water over Memorial Day? No. I wanted to get up to Lake Martin and do some fishing, but I didn't get a chance.
Weather shows Sunday, Monday, Tuesday, Wednesday, and Friday is supposed to thunderstorm.
Next week.
Next week, yeah. It was supposed to be the end of this week originally, but like I said, it's like slowly pushing the forecast back.
Yeah, well, I mean, they try their best, you know, predicting the weather. They say after 48 hours, it's a guess. I mean, there's a lot, the uncertainty goes way up. The best one I found out there for you guys' reference is called AccuWeather, A-C-C-U, weather. If you look at theirs and compare it to others, most of the time, AccuWeather is right. And by the way, they're a paid for service. If you want really detailed information, you pay them. I mean, countries like Israel do this. They're amazing as far as their accuracy. If you're willing to pay the money, they'll tell you pretty much what you're going to get in with a certain level of certainty, which is nice if you got a business like an airfield that you want to know for sure if that hurricane is going to kill you or not. And they're very good at that. Very good at it. Okay, next, TE. This is the one you pay attention to. All right, because almost everything's done. So this is the transverse electric TE mode. TE mode means EZ equals 0. Flesh.
Thank you.
So the EZ equals 0, and it's like this. This is still going to be dimension A. Do that little. This will still be the x-axis, and this is still the y-axis. This is still the z-axis. This is the cross-section of the guide. Dimension will be A. Height will be B. And if EZ is 0, the only thing you have is an 8C to worry about. Now, I don't want to keep doing this, it'll bore you, but I'm just going to tell you. You remember how, to get the original solutions, what I did is take two Maxwell's equations. You don't need to write this down, just listen. I took curl E is equal to minus j omega mu times h, and I took curl of h, and I said that was equal to just j omega epsilon times E in the phasor domain, because I assumed sigma was about 0. Then I took another curl of that one, stuck this in there, and voila, I came down with del squared of E plus omega squared mu epsilon times E equal to 0. Remember that? The term, and you're not going to be responsible for this, the term for this is called the Helmholtz equation. Or just wave equation. It's a general wave equation. It's a lossless wave equation. You don't need to worry about that. If instead of taking curl of E and then substituting curl of H in here when we had, curl of E, get a curl H over there. If we did it this way, if we took curl of H, you don't need to write this down, just appreciate what I'm doing. Curl of H is equal to j omega epsilon times curl of E, right? So what would I do next? I want one equation with just H.
Change curl of E.
I'd just take what? The curl of E here and stick it in there, right? Sure. So I'm going to go ahead and do it. It's going to be minus j omega mu times H. Now I've got one equation with one unknown, just H. Right? We're assuming epsilon, mu, omega are all known. So I have one, admittedly it's a vector differential equation. It's a curl equation. And now I can solve this thing. So I get this, and I use an identity. So it says that's the gradient divergence of H minus del squared of H is equal to, and this becomes J times J is going to be minus 1 times minus is plus 1. Now it becomes omega squared mu epsilon times H, right? You can almost guess what's happening there. Tell me about divergence of H. What does that mean? Better yet, what's divergence of B? How about divergence of D? What's the divergence of D? There's a famous law. It's the charge density, isn't it? Divergence of D is rho V. That's called the point form of Gauss's law. Remember, the integral of E or D dot ds was the charge enclosed. Well, the differential form is divergence of D is the charge density. Now, the divergence of B would be the magnetic charge density. What's the magnetic charge density for all macroscopic stuff? Always 0. There is no magnetic charge density. Therefore, divergence of B is equal to 0. Now, the truth is this. That means everything's in terms of magnetic dipoles. You've all heard that, I'm sure. At the very small microscopic level, if you go over to Europe, and if anybody's ever been around physicists that have been over CERN, in the super collider superconductors they've had, y'all hear of these things? These are gigantic tubes. They're cyclotrons, where they get mainly hydrogen nuclei, protons, flying around in opposite directions. They slam them together and look at the aftermath. Well, in fact, at super high energies, in the aftermath, they use what's called a bubble chamber, gas chamber. They see something that's an evidence of magnetic monopoles that exists for maybe 10 to the minus 15 seconds, just for an instant. All right, that gives them clues to the origin, how matter actually works in the unified field theory and all that stuff. But for us, in the world we live in, there ain't no magnetic charges. That would be rho m. It would be the magnetic charge. It's zero. All right, magnetic always have the field lines always close on themselves. D field close on what? The electric field, they start the positive, they end up at the negative. For magnetic stuff, you always got like a current or something, and they circulate through the center of a loop. So we get to this, that means that the divergence of B is zero, divergence of H is zero as well. That goes away. Now we have this, right? And I take del squared H to the other side, and I get this equation, del squared of H, and it becomes plus omega squared mu H, or mu epsilon, times H is equal to zero. That's a vector differential equation, second order derivatives, right there. Just identical in style to what we do with the E field. Remember the E field, we had del squared of E? I think I wrote it there, right there, right? Did all that. Then we do separation of variables, just like we did before. And we come up with, when we apply the boundary conditions, we get 8z is equal to some h0, some scalar value, but these will be cosine of m pi over a times x, and not sine, cosine of n pi over b times y times e to the minus j beta z times z. Beta z is still the same in all these. Now, here's the reason it's cosine. It could have been a sine, right? But here's the deal. When you take a look at the tangent value of the magnetic field, this is something I hope you get a hold of. Remember, now we've got H in the Z direction, right? Well, HZ doesn't go to zero on a good conductor. That's a good conductor here and here. HZ does not go to a zero. It goes to a relative minimum or maximum. It'll either be at its peak or its minimum, right? Actually, it'll be at the peak. All right, peak value. And what that means is the derivative of HZ with respect to the normal, with respect to Y here, with respect to X there goes to zero. And the only thing that will allow the derivative to go to zero are cosines here and here. All right, because if you have a cosine, you take a derivative in the X direction, you're going to get a sine. And a sine will go to zero, just like before we had sines going to zero. Remember, that's the reason we selected the sine function. Okay, guys? Now, you think about this for a while, if it's not real apparent, but it's very obvious when you look at it. So HZ has to be cosines. Now, from HZ, we can take, Wentworth does this, we can do the whole thing. We can take the curl of H, that's the Z component only, right there. So curl of HZ, and that would be equal to j omega epsilon times E. And in Dr. Wentworth's book, he does this. He can get all the E field components, and he shows this. And I don't, I mean, there are different teachers do different things. I do not drill you on telling me the variation of the E field for the 1-2 mode or anything like that for T, and then asking you for E, X, E, Y, and plotting. I don't do that. I can tell you what happens. Here in his book, he shows you on page 397 in the figure at the bottom of the page, the most important piece of information, and that's the electric field in the vertical or Y direction versus Z, the plot for the 1-0 mode. Now, that's the H field. He'll give you the E fields. This is the important one. From there, you can get the E fields. Once you have this, here's some important stuff that goes along with it. The lowest order mode is the TE10. That's the lowest order mode, period. It means that lowest order mode has to do with a cutoff frequency. And that means this guide, the cutoff frequency for the 1-0 mode will be C over 2 square root of epsilon relative. Square root, and it's 1 over A squared. Now, that's M. N is 0, so you don't need to include it. Or really, it's just C over 2 square root of epsilon relative A. And this is real important. Okay. This is the lowest operating frequency the guide can be in. Anything lower than that will propagate. Good on that, guys? Now here's the deal. The way waveguides that are rectangular are always designed is the first frequency that will propagate will be the 1-0 mode. Then the second frequency will be the 2-0, and then the 1-1. And the reason they do that is this. See, that's the 1-0 mode, right? I'll show you how they do it. I want you to get a hold of everything I'm saying here, because the last 15 minutes of class are going to be real important. All right, that's the 1-0 mode. What's the 2-0 mode? FC 2-0. Well, instead of 1 there, I'd have a 2, wouldn't I? I mean, I don't have the general formula. I'll put it here. FC in general for the M, N mode is C over 2 square root of epsilon relative square root of M over A squared plus N over B squared. That's it, period. So if it's a 2-0 mode, it would be 2 over A squared, right? And this would be 0. So this would be what? Well, this would really be 2, right? C over 2 square root of epsilon relative. Or it's really 2 times the first mode, 1-0 mode. You all see that, class? So if you got a 1-0 frequency of 1 gigahertz, the 2-0 will be 2 gigahertz. You all follow me on that? It's that simple. You follow me? Now, the next frequency that'll happen will be the 1-1 mode. And it'll be FC11. And that one is a little different because now it's C over 2 square root of epsilon relative. But now I'm going to have 1 over A squared plus 1 over B squared. Now what they do when they design waveguides, most of the time they do this. Matter of fact, all the time they do this, unless there's an extraordinarily, I don't know, an extraordinary reason not to. They'll always have dimension A, if this is dimension B, they'll have dimension A greater than 2B. And the reason is this. It will guarantee that the 2-0 mode pops up first and not the 1-1 mode. All right? If you look at this, just do the math on this one. If A, all right, is greater than 2B, then you can go through it. You can just pick numbers. It means the next lowest frequency will be 2 when this is 2, when this is 2, 0. And then finally, after that, then B, now you can't go to 3-1. Now you could have, or 3-0. Now it will become 1-1 will be the next frequency. And that's the way they're designed. They're designed for that for a reason. And I'll show you this. When you talk about the 1-0 mode, here's what happens. You get exactly, if this is EY you're showing here, EY will not vary with vertical position at all. You can look this up. All right, it won't. It'll only vary with horizontal position X. The reason is the vertical position, that's a 0 there. The end 0, cosine of 0 is 1. There's no variation with the vertical position, right? In other words, the E field, the E field in the Y direction here is the same thing as here, is the same thing as here, all the way up. Do y'all follow me on that? It varies versus the X position. And it looks like this, and this is exactly, this will be the actual cutoff frequency, the lowest order mode will be the cutoff wavelength by 2. So it's exactly a half wavelength long. So if I want to know what the cutoff frequency of a rectangular guide is for the 1-0 mode, the only thing I do is measure this dimension. And I say that dimension divided by 2 will be the cutoff wavelength. From that, I can get the cutoff frequency. Do y'all follow me on that, class? That would be the 1 ohm mode cutoff frequency. And it makes life a lot easier because you're going to see, when I show you the waveguides, you look at them and you, oh, yeah, that's the cutoff frequency for that. We'll do you some examples. I just want to try to give you an impression of how, when you look at a waveguide, what you should be looking for. And when you're in a discussion with somebody, they'll be talking about terminology and things. They say, oh, that's the cutoff wavelength. Suppose the width of this, just for instance, was 30 centimeters. All right, let's just do this. Talk about this for a second. So if this is 30 centimeters the width, right? Or 30 times 10 to the minus 2 meters, right? I said that was a half wavelength, right? Let's assume it's an air-filled guide. So if it's an air-filled guide, well, what's wavelength in general? We're going here free space, but what's wavelength? Isn't it C over F? Right? All right, so it's C over F. What is the frequency going to be for the 1 ohm cutoff? Well, I would take C, which is 3 times 10 to the 8th, right? Meters per second, divided by 3 times 10 to the minus 1, right? Correct? What do I see? 3's go away, I get 10 to the 9th, or it's going to be 1 gigahertz would be the cutoff frequency for the 1 ohm mode. Now, how big is 30 centimeters? Well, a meter is about that long, right? Third of it is about that. That's a wide waveguide. I'm going to say that. A gigahertz is a very low operating frequency. Now, 10 gigahertz, a half wavelength is about that. Y'all with me on that? And you start understanding about dimensions just by looking at the cross-section of the guide. I can figure out where I need to be frequency-wise to operate. When you see guides that's got millimeter height and width, now you're talking about 80, 90 gigahertz, maybe more. Okay. Trying to give you some insight. So that's how you get the frequency of operation of the lowest mode for a rectangular guide, the most common guides. Now we got to talk about, are you with me so far? Going to talk about now how fast this stuff propagates. Oh, I didn't say this, but I'm going to put the impedance too of the TE modes. It's different than TM. Here, and thank God it is, when we talk about guide impedance of TE modes, we talk about ZTE, but then it's for the MN mode. There can be a 1-1 mode here, but it'll have a different impedance. Now, that's equal to eta unguided divided by the square root of 1 minus FC over F squared. Now, for this to work and operate, you have to be over FC, and this would be for an MN, by the way. When I put in FC, I'm assuming it's for a given mode, an MN mode. The lowest would be for the 1 ohm. But when you have that right there, you can see one thing. The closer I get to cutoff, just take a look at this. When the frequency approaches the cutoff frequency, this is getting close to 1. 1 minus 1 is 0, right? This is going to infinity. You all see that? Right? In the other one, for the TM mode, the impedance is going to 0 instead. And a lot of times what they do is they just take this whole thing, instead of rewriting that over and over again, they create a constant K. And they say, let K be 1 minus FC over F squared. And then they'll just rewrite all these equations with that K. Now, I don't think Whitmore does that in his book, but it'd be nice if he did. And he doesn't spend a whole lot of time on rectangular guides, but I need to get through the velocity because I don't think he even shows it. Or maybe he does early on. Velocity is real important. Does he have that early? Probably does. Anyway, I'll show you this. Because one of the things you need to know is how fast things are propagating down the guide. And the phase velocity isn't the important one. He's got it on an equation on page 380, equation 710, but let me go through it, how you get it. And there's two types. There's phase velocity and energy velocity. Energy is the important one. Is there anything going on campus around that I don't know about? Or you? Here's what I found out in COVID from students that was useful to do. Students knew where you could get cheap things. You could buy things inexpensively. They knew what was closed down. They knew a lot more about what was going on in town on the ground than I did. And sometimes not all students did. So it was very useful to ask the students a question like that. Nowadays, the masks is over, right? Maybe everything's pretty much back to normal price-wise. But if anybody hears of a great deal on stuff, or anything like, I mean, they had deals on everything from food to masks and everything like that. Now I guess it's pretty much over. And but I still get takeout on when it's at a restaurant. Okay, back to this thing. So now we're going to talk about phase velocity. Without boring you, do you remember what phase velocity, how we got phase velocity in general for waves? Well, we knew the argument of cosine omega t minus beta z. The cosine omega t minus beta z was the phase of the wave, right? And we know the rate of change of the phase of the wave had to be a constant for phase velocity, right? And then we backed out, we said the phase velocity, or dz dt, was equal to omega over beta. That was the most general form. For our particular case, it still works. Only now it's beta in the z direction. It's not the free space beta. So now it's equal to omega, this is phase velocity, by the way, omega over, and it would be beta unguided, right, times square root of 1 minus fc over f squared. Remember that fc has to do with the mode. It's different phase velocities for different modes. Y'all with me on this, guys? Now, beta unguided is just omega times square root of mu epsilon. Fc has to do with the mode number, is equal to c over 2 square root of epsilon relative times the square root of m over a squared plus n over b squared. Now, I know I have to be above fc in order for propagation to occur. Means this is less than 1. But when I get very close to 1, what happens to the phase velocity? Going to infinity, isn't it? Y'all with me on that? What does that actually mean? Let me try to explain this. If I take a cross, or if I look down the guide and split it in half, and I'm just looking right down the center of the guide, this is the z-axis here. I'm not going to do this. One way of explaining phenomena in guide is a superposition of two wavefronts. Frankly, if you have a wavefront progressing this way and reflecting and then going like this, all right, you can actually take one that way and then one the opposite way. And you can do this, and you can, in fact, that will be a solution of differential equations. Right? It is. It works. But they're propagating at a given angle. They're basically going at some angle of incidence. And I guess what I can do is show you this, some angle of incidence. Now, as that angle approaches 90 degrees, or as the thing's moving down, it's moving at the speed of light. It's moving at the speed of light in that material. But when the wave's just bouncing like this and that angle's getting bigger and bigger, right? When all of a sudden, I should say, smaller and smaller, when it's bouncing just straight up and back, there's no net progression of the wave down the guide. The wave is just bouncing up and down like capacitor plates or something like that. And that's when you're at cutoff. All the energy just bounces up and down, nothing propagates. That's the cutoff. So when we talk about phase velocity, what we're actually talking about is this. Please watch this. This is important. If you thought about a wave front like this, as a matter of fact, let me just draw it freehand. If you got a wave front coming in at a shallow angle here, right? You can see that this point, as this thing's moving in this direction, well, this point's moving in this direction. But for a given distance traveled there, this would be a longer distance. But this would be the same phase fronts, right? Say this is 0, this is 180 degrees. Do y'all follow me? Now that point where it's intersecting and moving at a constant phase is the phase velocity, how fast it's moving, right? Well, what happens if this angle gets more and more vertical? When it starts coming in like this. Remember, the wave front's moving this way, right? Well, then a short distance here would mean a huge distance here. Y'all see that? Think of waves crashing onto the beach, right? If the waves are basically moving parallel to the shore in that direction, the crest of the wave is moving at the velocity of the wave itself. But if you look at the intersection of the wave and the shoreline, as the wave's starting to make less and less, and think of that as like waves bouncing the shore, then the velocity of the crest of the wave is much, much less than the velocity of that breaker moving, the actual wave action on the beach. Do y'all follow me on that? Well, you're not, okay, I'll help you afterwards, but I want to finish this thought. So phase velocity has nothing to do with energy, but here's the thing. Phase velocity times group velocity or velocity of energy is equal, that will always be equal to the actual, this thing, omega over beta unguided squared. So when you have the phase velocity, you take omega squared over beta squared and divide that by the phase velocity, you get the group velocity. They're inversely proportional is what I'm getting at. The product will always be omega over beta unguided squared, like free space phase velocity.
And you said group velocity was energy velocity?
Pardon me?
You said the group velocity is energy velocity?
Yeah, it is. That V sub G is equal to group velocity. But it's also the velocity of energy. And that's the only thing that's important. Let me just take a moment, one last thing. I've tried to do this thing in a meaningful way. Can you all just look up here? Assume that's a shoreline, right? This whole top portion here. All right, if I got a wave moving this way, coming at a certain rate, it's going in that direction with velocity v. Y'all see the point on the shoreline is going to be where the actual wave crest intersects is going to be moving faster than the crest of the wave in the direction it's propagated. Y'all see that? Well, that point is the phase velocity. It's like the phase velocity we talk about in a waveguide. That's what it is when it strikes. And it means nothing as far as real energy. It's simply, see, you get phase velocity much greater than the speed of light. People say it's impossible. Yeah, no, it's perfectly possible because this phase velocity is just an intersection of 2 points, a phase point that's moving. Well, no mass, no energy is being transmitted. The only thing that's happening is you've predefined something as a phase phenomena, and you're looking at the crest intersecting another surface. But nothing's moving. It's just, nothing's moving greater than the speed of light or anything like that. So just keep that in mind. And people often get fooled with that stuff. So nothing can move faster than the speed of light in a vacuum. That's energy or mass. However, you can have phase itself move faster, but nothing's really moving. It's just a point. All right, I'm over the time. If you got questions afterwards. Hey, if you got time, walk up with me to 423 and I'll show you some waveguides. You want to see them? Because I think